Welcome to Electrical Engineering with Excel. In this video, we will look at some Visual Basic for Applications user-defined code in Excel to select the best fit resistor values for a voltage divider. This is only for the selection of 1% tolerance resistors. Although 1% tolerance is good, arbitrary selection of values can result in the divider's output being less precise than it could be. Let me show you an example. Let's design a voltage divider using 1% resistors. Bear in mind this represents an unloaded divider. In other words, it feeds into a high impedance, such as an op-amp, comparator, or other circuit that will have negligible effect on precision. The input is 12 volts. The output is 1.595 volts. Here's the standard textbook resistive divider equation. Let's set the divider current to 100 microamps. R1 will be Vin minus Vout over the divider current, which comes out to 104.05 K. The closest E96 value is 105 K. R2 will be Vout over the divider current, which comes out to 15.95 K. The closest E95 value is 15.8 K. Putting those values in the divider equation gives us 1.56954 volts. The percentage error is 1.5965%. That's how far off our divider is, with the resistors being 0% accurate. Just the spacing between the intervals of the resistor values can result in greater than 1% before the additional tolerance of the resistors even come into play. The selection for the divider current is usually quite arbitrary. In most cases, the total resistance of the divider can be selected over a wide range of values. We can write software to find which two values in the E96 set are most accurate for the specific division ratio desired, and let the current in the divider be what it may, within reason, of course. If you haven't watched my computing standard component values video, the math here may not make much sense. There should be a link up top. Let's do a quick review of the math associated with the E96 values. Each value in the series is a rounded version of the nth root of 10, where Vn is the rounded values, m is the E-series group size, and n is the specific integer value in the series. For the E96 series, the common ratio of the geometric progression is the 96th root of 10, or 1.024. The series value is that common ratio raised to the nth power, rounded to two trailing digits. For example, to compute the 13th value in the series, raise the common ratio to the power of 13 and round to two trailing digits, which comes out to 1.37. Here it is in the chart as the 13th progression. To make this work, we need to know how many intervals there are between the top divider resistor and the bottom. We will apply that offset and scan all the values and see which one gets us the more accurate answer. We need to solve for n. We take the log base 10 of each side of the equation and apply the logarithm power rule, which moves n to the front of the equation. Then arranging to solve for n is simply the log of Vn over the log of the common ratio r. Let's determine the closest series value. To 1.522, which comes out to be 17.5118, we need the integer n, and the 17.5118 is closer to 18, so a simple round function does the trick. Here in the chart, the 18th value is 1.54. The ratio of the resistances may be large, so we'll need to scale the ratio to less than 10 and greater than 1. Here's the E96 base values. In the next tier of 96 values, with that upper red pointer being 26 intervals above the blue one, using a for loop, we can move these pointers up one at a time and reassess the accuracy of the two resistance values against the ratio. When the upper pointer reaches the 96 value, it will go up into the next set of 96 values. We will not use a loop of 192 values. we will just simply wrap the upper pointer 96 steps back. If the best fit value is in that region, the top resistor value will get scaled to 10 times the value of the one in that pointer. Here's the code. All of this first part is just dimensioning. I'm calling the function BVFD for best fit voltage divider. It has 3 arguments: the input voltage, the output voltage, and the low side voltage. The low side voltage allows the divider to float and not be tied to ground. The low side could, for instance, go to a negative voltage. The first one is the return value array, which is a 5-element array returning the 2 divider resistor values, so its argument is 1 to 5. The function will only return 2 resistor values in 1 and 5. 2 through 4 will be nulls, so the values will be spaced out in the spreadsheet in a visually revealing manner. You'll see that later. Next will be an array that holds the 96 standard base resistor values as a double. N will be used as the integer for the index of the 96 resistor value. Since we are assigning a specific number of intervals above another pointer, we will need the ratio to be above 1. If it comes out below 1, it will be reciprocated. If this flip occurs, we have a Boolean flag called ratio flipped, so that at the end we can swap the resistors to make the ratio consistent with the input ratio. Since we are working with the base values, we need to scale down the ratio to a single digit with decimal places. The scale factor is an integer representing how many times 10 the ratio got scaled down to. Next will be K, geometric progression's common ratio, which will be a double. Then R, a double that represents the ratio of the 2 resistors. Best fit is the difference between the desired resistor ratio and the best scan pair ratio. X is an integer for the index of the array of 96 standard values. Y is the index of the upper pointer that is offset by the calculated number of intervals apart from X. Top R is the selected resistor value for the top resistor, and bottom R is for the bottom. Both are doubles. Temp is a double that's used to temporarily store a resistor value to allow it to be swapped with the other. Last Y is an integer that stores the last Y value that was best. If it's above 96, we will multiply the upper resistor's value by 10. Now we will initialize some variables. The ratio flipped is set to false. K, the geometric progression common ratio, is set for the E96 series as 10 raised to the 196th power. Next, use a for statement to load the 96 base resistor values in the resistor values array. Notice N starts at 0 for the calculation of the resistor value, which is K to the nth power, rounded to 2 decimal places. The array number is N plus 1 since the array index starts at 1. Now to calculate the ratio between the resistors, we will divide Vn minus Vout by Vout over Vlow. We want the ratio to be above 1, so if R is less than 1, reciprocate R. Then set the ratio flip flag to true and end if. We need to determine how many digits the ratio is so we can scale it down to 1 decimal digit. Just taking the integer value of the log of the ratio R returns the number of digits. It's important to know the VBA log function is base E and not base 10. Therefore, we must use the log base change rule to change it to base 10. We simply divide the log base E of the number 10. We then divide the ratio R by 10 raised to the scale factor number. That would convert a number like 699 into 6.99. Now it's time to calculate how many E96 intervals apart the ratio is. From the math we looked at earlier, it's the log of the ratio over the log of the geometric progression common ratio. That gets rounded to 1 digit. The best fit number is reduced each time a better set of resistors are found. Here it is initialized to a large number as a seed. Now we will do a for loop for 1 to the 96 resistor values. Y will be the index of the upper resistor interval, which is the lower index X plus the intervals apart offset. While in the loop, if Y becomes greater than 96, we need to make it wrap back by subtracting 96 from itself. If the fit for the next resistors is better than the last one, then store the values. Ideally, the ratio of the resistor value index of Y over the resistor value index X would exactly equal R. It takes the absolute value of that because we don't care which direction it's off. If that difference is less than the last best fit number, the new best fit is set to the new difference. Then load the best so far resistor values into the variable top R and variable bottom R. Now set the variable last Y to the Y index so that we can test it for being greater than 96 later. End if and next X. Now it's time to rescale the values back up if they were scaled down initially. If the last Y is greater than 96, the top R will get multiplied by 10 raised to the scale factor plus 1. Else the top R will get multiplied by 10 raised to the scale factor and end if. If the inputted ratio got reciprocated, we need to swap resistors. Set the temp variable to the top R and set the top R equal to the bottom R, then the bottom R equal to the temp, and end if. Finally, we need to load the return value array with the resistor values to be returned in a spill array. Return value 1 will be the top resistor value. Return values 2 through 4 will be null, and return value 5 will be the bottom resistor values. Spill arrays spill to the right in a row by default. We want it to spill down across a column, not a row, so we transpose it with the application transpose function and set the function name equal to it. Then end function. Here's the spreadsheet. As usual, I've done data validation on all the inputs. The input voltage must be greater than Vout. Vout must be less than Vin and greater than Vlow. Vlow must be less than Vout. This could be used with a negative number if needed. Here are the entries for the power rating of the resistors, which must be greater than 0. Then a derating factor that must be between 0 and 100%. This is typically 50%. Here's the cell where the BFVD function is used. Notice it spills down 5 cells with the ones in the middle empty. I wanted the resistor values to align with the schematic. Here's the actual output voltage calculation. This cell calculates the error between the desired and the nominal output, not counting the tolerance of the resistors. And here's a table with resistor values 7 decades above the base values. This helps you decide which values to choose based on the power rating of your resistors. I set conditional formatting to strike through and color red the ones that come out greater than the derated power. I also set conditional formatting to show values above 1 megaohm, which are not normally available in a 1% tolerance. Remember, in our initial example, we had 12 volts divided down to 1.595 volts. The resistors we chose gave us over 1.5% error. Our code has found resistor pairs that give us a 0.00195% error now. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.